Dear students, I welcome you in this lecture from the chapter Linear Programming Problems. In this lecture, we are going to solve some linear programming problems of maximization type. Let us see examples of linear programming problems which are of maximization type. So first example which we are going to see is this: maximize z is equal to x plus 3y. This is objective function. Maximize, you can see that this is problem of maximization. Maximize objective function z is equal to x plus 3y subject to linear constraints. Two linear constraints are here. 2x minus y is less equal to 4 and 2x plus 3y is less equal to 12. Then we have non-negativity constraints which are x is less greater equal to 0 and y is greater equal to 0. So non-negativity constraints assure that the answer of the problem, linear programming problem, that we will obtain will always be in first quadrant. It will never be in second, third or fourth quadrant. So answer will always be in first quadrant. This is assured by non-negativity constraints. X is greater equal to 0 and y is greater equal to 0. These are called non-negativity constraints because it states that x as well as y coordinate of solution of any linear programming problem will always be non-negative. It is greater equal to 0, means either 0 or greater than 0, that is positive, but it will be never be negative. So non-negativity constraints. In the previous lecture we have seen that any linear programming problem has three parts. First part is objective function, second part is linear constraints, and third part is non-negativity constraints. So this linear programming problem, in this linear programming problem you must be able to identify what is objective function. What is objective function? Z is equal to x plus 3y is objective function here. What are linear constraints? Linear constraints, these are two linear constraints. 2x minus y is less equal to 4 and 2x plus 3y is less equal to 12. What are non-negativity constraints? X is greater equal to 0 and y is greater equal to 0. These are non-negativity constraints. Okay. Now, let us see how to solve this linear programming problem. Solving linear programming problem means to obtain those values of x and y at which objective function z is equal to x plus 3y will have maximum value such that all constraints or all inequalities get satisfied, linear constraints as well as non-negativity constraints. So that is the meaning of solving linear programming problem. So first step in solving linear programming problem is to plot lines. How to plot lines? We have already seen. Now which lines to plot? You don't have to plot this line. In fact, you can't plot this line. This is not a line. This is not equation of line. You have to plot these two lines. These two lines are already plotted. They are axes, x-axis and y-axis. X is equal to 0 and y is equal to 0. These are nothing but x and y axis. So first step consists of plotting lines. Now you have to plot two lines in this case because there are two linear constraints. Which are two linear constraints? First is 2x minus y is equal to less equal to 4, and corresponding line will be 2x minus y is equal to 4, and second line will be 2x plus 3y is equal to 12. So how to plot lines? In the very first lecture we have seen. If you are not able to follow that, I will request you to watch the first video once again. So in order to plot lines, we need 2 points, one on x-axis and one on y-axis. So here point on x-axis will be 4 upon 2, which is 2, and point on y-axis will be c upon b, that is 4 upon minus 1, which is minus 4. So you can see that we have 2 points here, 2 and minus 4 point is going to be here. Okay, so let me change the coordinates so that we will be able to get. I'll put here x as say minus 5 and then we'll graph it. Okay, so point on x-axis will be minus 4 and point on point on x-axis will be 2 and point on y-axis will be minus 4. Then for second line, point on x-axis will be 12 upon 2, which is 6, and point on y-axis c upon b, that is 12 upon 3, it is going to be equal to 4. So thus we have two lines. One line passes through point 2 and another line passes through minus 4 respectively on x and y axis, and another line passes through point 6 on x-axis and point 4 on y-axis. Let us see the plotting of these lines. So I could have an utility to plot these lines. Okay, here it is. Okay, so here you can see we are having two lines, 2 minus 1, 2x minus 5 is equal to 4 and 2x plus 3y is equal to 12, and these lines passes through the point 2 and minus 4. This is the point 2 and 4. Let me erase this, and the another line which we are having, is it represented in blue color? Its equation is 2x plus 3y is equal to 12. Okay, so here we have these lines and corresponding points. Let us come back to the linear programming problem. After plotting the lines, we have to determine feasible region. So second step in solving linear programming problem is to determine common feasible region. Second step is to determine common feasible region. First of all, note that non-negativity constraints assure that solution of any linear programming problem will always be in first quadrant. So our shaded region will always be in first quadrant only. Okay. Now for determining common feasible region, you need to refer to the previous lecture where we have seen how to determine feasible region for linear constraints. So first thing, note that feasible region will always be in first quadrant. Secondly, we have to determine common feasible region of all constraints. So let us see step by step how are we going to determine feasible region for each of the constraint. So here we have 2x minus y is less equal to 4. Refer to the video in which we have seen how to determine feasible region. This is the line 2x minus y is less equal to 4. Okay. And point on x-axis is 2, this point I am referring to, and point on y-axis is minus 4, this point. So this point I am going to refer. So this is the required line. 2x minus y is less equal to 4. Now in order to determine feasible region for this, you have to substitute x and y as 0. So 2 into 0 minus 0 is less equal to 4. That comes as 0 is less equal to 4. Whether it is true or false, it is true. And what is the feasible region? Origin side. Again, we have to restrict ourselves to first quadrant due to non-negativity constraints. So this is going to be the feasible region for us. If we restrict ourselves to first quadrant, then this is going to be the feasible region. Okay, for first line. Now, why we are shading origin side? Because inequality is true, 0 is less equal to 4. In case it is false, we could have shaded non-origin side, but here we have to shade origin side of this line. Now second inequality, 2x plus 3y is less equal to 12. Again put value of x as 0, value of y as 0, because origin has 0, 0 coordinates. Check whether this inequality is getting satisfied or not. It is getting satisfied, it is true, because 0 is less equal to true. Again we have to shade which side? We have to shade origin side of this. Again in first quadrant we are going to restrict ourselves. So this is the line, green line, and we are going to shade origin side. I'll put it as plus sign everywhere in order to distinguish ticks and plus. Okay, so we have to determine common feasible region. Common means where both ticks and or plus signs are present, both ticks and plus. So you can observe that this is going to be our common feasible region, this one, where both ticks and present are there. So whatever we have shaded in white region, this is the common feasible region. This is the common feasible region which we have determined. This is second step. This is common feasible region which we have determined. Now third step is is to determine vertices of common feasible region. Determine vertices of common feasible region. Vertices of common feasible region. How to determine vertices of common feasible region? Most of them are determined or already determined while plotting lines. So you can see we have origin, we have point 20 on first equation, we have point 04. Now the only point which is to be determined is 3, 2. So how to determine this point 3, 2? How are we getting 3 and 2 as vertices of this? It may be geometrically clear, but we have to determine it precisely by algebraic methods. And we have seen in the second lecture how to determine intersection point of two lines. So note that we are having two lines here. 2x minus y is less equal to 4 and 2x plus 3y is equal to 12. So for the time being, you remember these two equations, 2x minus y equal to 4 and 2x plus 3y is equal to 12. Recall how we can obtain intersection point of these lines. Here is the way in which we have seen the method to obtain intersection point of two lines. So, two equations, 2x minus y is equal to 4 and 2x plus 3y is equal to 12. A1 is 2, B1 is minus 1, C1 is 4 corresponding to this. 2 minus 1 and 4. A2 is 2, B2 is 3, C2 is 12. So here A2, B2 and C2. You might, by this time, you might be remembering this formulae. If not, remember, try to remember these two formulae, X and Y. Substitute values of A1, B1, C1, A2, B2, C2, do calculations, and within 2 or 3 steps, you will get value of X equal to 3 and value of Y equal to 2. So intersection point of these two lines, as you can geometrically see, 3, 2. X is having value 3 and Y is having 2. So this is how we determine intersection point of two lines, and same is going to contribute for the vertex of common feasible region. Thus, we have vertices, four vertices of common feasible region A, B, C and D. A we have determined. Just now we have seen how to obtain intersection point. It is 3, 2. B 20, C 04 and D 00. So these are four vertices of common feasible region. Now the last step, fourth step. Fourth step is to obtain values of objective function at vertices. So values of vertices, values of objective function at vertices. Objective function at vertices. Which vertices? Vertices of common feasible region. Okay. So how to obtain values? Simply substitute values of x and y. So what is objective function here? Objective function is z is equal to x plus 3y. So value at first point is 3, 2. So 3 plus 3 into 2. So 6 plus 3, and that is equal to 9. This is how we get 9. Now next vertex is 2, 0. Again substitute here x as 2 and y as 0. So what value we will get? 2 plus 3 into 0, that is 2 plus 0, which equals to 2. Next point is 0, 4. This is 0, 4. This vertex we are talking about, common feasible region. Substitute x as 0 and y as 4. So what you will get here? 0 plus 3 into 4, that is 12. So 0 plus 12, we get 12. And last point, this is origin which we are getting. Substitute x as 0 and y as 0, so it will be 0 plus 0, and we will get 0 plus 0 as 0. So 4 values we have obtained: 9, 2, 12 and 0. The original problem was of maximization. So identify the maximum value. Which is the maximum value? It is 12. And final answer is the objective function has maximum value 12 at the point 0, 4. So value maximum value is 12 and it is obtained at the point 0, 4. At 0, 4, at the point 0, 4. So this is the final answer of this problem. Maximum value is 12 at the point 0, 4. I'll request you to solve more examples on maximization type of linear programming problems. That's all for this lecture. Thank you.